Hello, everybody, and welcome to Dark Matter Day. Make it, break it, shake it. Welcome to those of you watching on Zoom, and hopefully welcome to those of you watching on the Bulby Facebook Live. My name is Lauren, and I work at the Science and Technology Facilities Council, and I will be hosting our event today. We're delighted to be running this joint event, bringing together SNOLAB, STFC Boulby Underground Laboratory, the INFN, the University of Edinburgh, and the University of Manchester to celebrate Dark Matter Day. Since the postulation of dark matter, scientists have been trying to learn more about it in one of three ways: making it, breaking it, and shaking it. Now, before we begin, there's a few bits of housekeeping that I'd like to share with you. So we are recording this webinar, and we will share the link after the event has ended once it's been processed. For those of you watching live on Zoom, we will have a live transcript enabled, which can be hidden or shown using the live transcript button on laptops, but it can't be hidden on mobile devices, but it shouldn't stop anything that you are able to see. We will share any useful links that we have and any messages in the chat throughout the session, so do keep an eye on it. But if you do have any questions or messages for us during the event, you can pop them in the Q&A. So I can see some people have said, have already using that Q&A function, so fantastic. Great. So I will now head on to the running of the event. So this is our Dark Matter Day event, Make It, Break It, Shake It. And in a moment, we will begin with a short introduction to dark matter by Nobel Laureate Art McDonald, before hearing from Caterina Doglioni about how we are trying to make dark matter at the Large Hadron Collider. And then Alberto Oliva will then explain how we are trying to find dark matter by breaking it. And then Jita Hall will explain how they're attempting to shake it at SNOLAB. After this, we'll have a short comfort break before traveling deep underground to visit two of the most fascinating and unusual laboratories in the world, located in working mines in Canada and the UK. Both SNOLAB and the STFC Boulby Underground Laboratory are helping in the search for dark matter, as well as many other types of amazing science. And this is a great opportunity to learn more about them and meet some of the amazing scientists, engineers, and technicians that work in these unique locations. We'll then finish up with a panel discussion and Q&A session to answer any of the questions that you might have throughout the session, so do send them in. And if you have any questions for any specific speakers, please do put their name at the start of the question, and then we'll be able to answer those for you at the end. So to give us an introduction to dark matter is Art McDonald. Art is a Nobel Laureate and a Professor Emeritus in Physics at Queen's University. Since 1989, he's been the director of the Sudbury Neutrino Observatory experiment, and in 2015, he received the Nobel Prize for SNO's part in solving the solar neutrino problem. Art is a member of the Dark Side collaboration searching for dark matter, and he will now give us a short introduction to dark matter. So, Art, over to you.
Okay, very good. I was just about to share my screen,
Perfect.
So give me a moment to do that. It's a pleasure to see this international cooperation, which we do between the laboratories and also many other laboratories and many scientists across the world. So let me start with my presentation. And so what is dark matter? It's pretty unusual stuff, but it is amazing how much we have learned about the stuff that we have had experimental results on so far, and stuff that makes up us and stars and things like that. And we've learned a lot from measurements in physics, astronomy, and also in how it all fits together in the theory of cosmology, which is how the world, how the universe has evolved. So dark matter is one of the elements of this theory. And I'll show you in a moment how we understand that it is a necessary part of our total composition of the universe, although we've only really learned about it through its gravitational effects so far. What we'll talk about today is how we may learn more about it by determining how it interacts with ordinary matter like us. So let's start by reviewing the physics of fundamental particles to show what we know and why we think that dark matter may be something completely different. So the current theory of elementary particles, usually referred to as a standard model, classifies basic particles that make up our universe as quarks or leptons. Quarks are in 3 generations, as are the leptons. The ones that we're familiar with are the ones that make up our protons and neutrons that sit inside the nucleus of our atoms. Those are the up and down quarks, as they're referred to. Charmed, strange top and bottom quarks are heavier versions of the same thing that have been observed in high energy experiments with accelerators and in cosmic rays. The 2 up and down quarks form the protons and neutrons, and then an atom is formed by those protons and neutrons being in a nucleus at the center of the atom with electrons, which you see down at the bottom here, going around the nucleus and forming the chemical elements that you're familiar with. There are other particles referred to as neutrinos that have counterparts with the electron and its heavier partners, the muon and tau particles. Used in some forms of radioactivity, but naturally emit neutrinos, believe it or not, in very, very small quantities. And they're also produced in the core of the sun by the nuclear reactions that power it. And in fact, the SNO project was observing those neutrinos and from the measurements, inferring that they have a small mass, along with experiments done in Japan that did the same thing for neutrinos produced in the atmosphere. But just to give you a feel for how little neutrinos interact with things, there are billions coming from the sun at the present moment. With a detector the size of a 10-story building, we observed 1 neutrino an hour with the Sudbury Neutrino Observatory original experiment. The blue on the particles on the right are what we refer to as the force carriers. Photon for the electromagnetic force, the gluon for the strong force, the Z and W particles for the weak force. And in addition to that, we have the graviton for gravity, which is not shown in this figure. The Higgs boson gives mass to all of the particles except neutrinos that appear to obtain their mass with a different mechanism. And for each of these particles, there is an antimatter particle that has been observed. And we think that in the early universe, energy was converted into mass and antimass in equal quantities. And so particles and antiparticles would have been created out of the energy that came forth in the original Big Bang. Dark matter particles, based on what we've seen so far, do not share any of the properties in common with any one of these particles, and therefore we think it must be a new form of matter. That's why we want to observe it and understand its properties, and that's what today is all about. Now, we have quite a robust theory of how the universe has evolved since the original Big Bang about 14 billion years ago. And this has come about from many measurements in physics and astronomy, along with the theory of cosmology. And let me tell you a bit about that, and then the others will tell you about the experiments we're doing today to try to understand more about dark matter. So here's the overall story of today of what we think the universe evolution looks like. On the order of 14 billion years ago, there apparently was an enormous explosion. We only really know what we can learn from the information following that explosion. We don't know what happened before it. We don't know what caused it, because it's very difficult to observe anything. And scientists base their their judgments on things that they are able to observe and measure. The theory suggests that that explosion liberated a tremendous amount of energy. And in about first 10 to the minus 43 seconds, there was a tremendous expansion referred to as inflation, where the whole universe went from the size of an atom to the size of a grapefruit. And then it continued to expand after that. At the point where about 10 to the minus 32 seconds, when you're still dealing with 10 to the 27 degrees centigrade as the total temperature, everything has been created from energy in the form of matter, equal amounts of protons, of particles and antiparticles, quarks, neutrinos, and electrons and their partners. And as the universe cools off, then the quarks begin to coalesce into neutrons and protons at about 10 to the minus 6 seconds. After about 3 minutes, we're at the point where those protons and neutrons can form nuclei. After about 300,000 years, you actually have the electrons joining on to form neutral atoms. And finally, at that point, light can shine through. And that has been a very big element of our ability to understand what has happened that leads to this narrative I'm describing to you. The so-called cosmic background radiation is the light that has come through after about 300,000 years of evolution. It's about 2.7 degrees above absolute zero now in terms of the way it has cooled off. And it's one of the things I'll talk to you about in terms of the information that we obtain, which leads us to this theory. Another big question is the influence of dark matter. I'll show you that we understand that dark matter makes up about 5 times the mass of everything glowing that you see when you look out on a starry night. There's about 5 times as much mass between the stars as in the stars and galaxies themselves. That influences significantly the formation of galaxies, stars, and the coalescence of those galaxies into the universe as we see it today, about 14 billion years after the original Big Bang. Now, how do we know that? Well, one of the things that we're able to observe is this 2.7 degree radiation. And that's been done with exquisite measurements, originally on Earth and most recently in extremely good satellite measurements. The picture on the left shows you the variation in the amount of this radiation. The variation is only about a part in 100,000. But that variation can be expressed, in this case, its variation across the sky can be expressed in the way shown in the figure at the bottom. These are actually polynomials of order L as plotted along the horizontal plot, and the amplitude in the vertical direction. If you look closely, you can see little dots, which are the data. And the average of the data is in fact the red points. But the blue line that goes through them is a theory of how the universe has evolved, involving ordinary matter and dark matter that has cooled off itself to a very low temperature. And the fit you can see is extraordinary. And there are really only 6 parameters in the fit. It's an amazing accomplishment. But it suggests very clearly that there is about 5 times as much dark matter in mass as there is ordinary matter. And that's borne out by looking at galaxies like ours, like the Milky Way, which is a spiral galaxy. You see another one, it's actually, I think, a cluster of galaxies, but it's in a form that kind of looks like a cinnamon roll. And the reason we see a patch across the sky called the Milky Way is that we're looking at the edge of it. So we're looking through it. But if you plot the velocity of matter as a function of radius, you see this plot in the upper right. And what you find is that you can't explain it with the amount of matter that is there that is glowing. That would be the line labeled as disk. What you need is about 5 times as much mass in a form that's referred to as the halo, which is thought to be dark matter. It's not glowing, you don't see it, but it influences it through gravity. We come to a similar conclusion in this factor of 5 more mass in dark matter by looking at the universe as a whole, which can be done remarkably by lensing light from behind, from a bright source behind other matter, producing, due to the laws of general relativity, images that are shown as the bright blurry images on the left in this telescope picture. A similar conclusion is drawn that there's about 5 times as much mass in dark matter. And finally, in terms of the fact that it is quite weakly interacting, it's quite a beautiful example of this. There are many ways in which that's concluded, but here you see two clusters of galaxies that have collided, and they've already passed through each other. But what you can see is that the ordinary matter, which is imaged in X-rays, is the pink material, the pink section in the center. If you do this gravitational lensing process to see the total mass, or the remainder of the mass other than the X-ray imaged material, you see the two blobs that are in blue in this picture. It's quite clear that the dark matter has moved through much more quickly, much less impeded by collisions, which is what happened to the pink ordinary matter. And so our conclusion is that dark matter interacts very weakly. So overall, putting all this evidence together, one concludes that at least one way to describe dark matter is in the form of particles that are weakly interacting and are massive. Massive comes from their influence on how material forms in the formation of galaxies and so on. So weakly interacting massive particles, or WIMPs. And scientists have a certain sense of whimsy, and WIMPs is a fun term to use. So that's a major topic for today. And we're a bunch of geeks looking for WIMPs, you might say, if you really want to characterize today's discussion. Sorry for that description of my colleagues. I'll just accept that for myself. Major topic for today. There is another candidate, which is particles referred to as axions. They have very different properties, and we're not going to try to address them in our discussions today. So our final picture of how the universe is made up has 3 major components: matter, us and the stars; dark matter, which we've just discussed, and a final one referred to as dark energy. And it's quite remarkable how the 3 of them fit together, and they also fit in those models of cosmic microwave background. Dark energy has been inferred by studying supernova at the farthest distances in the universe. And they found, when measuring them, that they are accelerating more than is expected. They're able to measure how fast they're going through the redshift, and how far away they are, because they're a very standard supernova that always give out a certain amount of light, and they can just tell by seeing how faint they are. This requires that there's a repulsive force added to the attractive force of gravity. And so what you've learned in school for years, that gravity is always an attractive force, is violated to a certain degree, not here on Earth in a noticeable way, but in terms of its influence and how the universe has evolved. And that's also the subject of very different experiments from what we're doing for dark matter. So we're after dark matter. And how do we go at it in terms of trying to get new properties determined? Well, we're in a universe composed of matter. We want to use that matter to try to observe more properties of dark matter. And so we have to have essentially an interaction between the dark matter and our experiments made of ordinary matter. And so there are predictions of what that dark matter might be, ways of expanding the standard model in acceptable ways to include dark matter. Too many theories for us to discuss them in detail at all today. But the make it, break it, and shake it you're about to hear about are basically ways of how dark matter interacts with ordinary matter. Perhaps by creating enough energy in ordinary matter, you can make it. Perhaps by observing it to decay, or perhaps interacting with itself, referred to as annihilation. You may see ordinary particles that you can detect, and that'll be discussed under Break It. Finally, it's more complex than this, but essentially what one is looking at is having the dark matter hit atoms and having them recoil like a billiard ball. And that's the shake it part of our discussion. So I'm going to turn it over to my colleagues who are experts in these three categories, and hope that you'll have fun listening to how they're going to do these experiments. Thank you very much.
Amazing. Thank you so much, Art. That was incredible. It's so lovely to hear you speak. Hopefully, if you have any questions, you'll be able to pop them in the Q&A and we will answer them for you. But next up, we have Caterina Doglioni. Caterina is a professor of particle physics at the University of Manchester with a joint appointment at Lund University. Her research is driven by finding out more about the known and unknown constituents of matter using big science tools. And she is a member of the ATLAS experiment at the Large Hadron Collider. And she will now tell us a little bit how we are trying to make dark matter at CERN. So Caterina, over to you.
Thank you very much. And let me share my slides now. And that is here. Okay, so yeah, I'll tell you about how we try to make dark matter. And the spoiler is that we've not managed yet, at least it's not in the quantity that we wanted to see it. But at least I'll explain you how we're actually trying and what we're doing. How do we make dark matter? And we start with asking ourselves what we know about dark matter. And well, the screen didn't actually go blank. We do know quite a lot about dark matter. And this is something that we have learned also from Professor McDonald's talk. We know that dark matter constitutes most of the matter in the universe. And this is, if you just take the matter part of our universe, 85% of the matter in the universe is dark matter. And this is called the relic density of dark matter. And this relic density that we're seeing can be explained with a new particle. It would be very, very nice if there was a simple explanation that this was, and this explanation was the WIMP, a particle that interacts only weakly with non-matter, because otherwise we would have seen it before. And the other nice thing about this WIMP hypothesis is that it has mass in a range of current experiments. Of course, it's not the only explanation. There's many other kinds of particles, many other kinds of experiments that can explain dark matter. But I'll focus on this right now. So for the dark matter that we can see today, we know that it's 85% there. Well, we know that from astrophysical measurements, from gravitational measurements, we know that there's relic density there. And that means something for this dark matter particle. It means that it's dark. Well, we can't see it, but it also means that it's stable. So it's still there. But how did that 85% of the universe come up? How was it made? And a lot of theories show that dark matter particles could have interacted with known particles. And it's via this interaction that we're trying to make dark matter in the lab. So we're trying to collide at very high energies some known particles, and we're trying to make dark matter particles after this collision. And what are our tools? Our tool is the Large Hadron Collider. So this is a big ring And what you see there, it's actually a lake, Lake Geneva. The mountain in the back is Mont Blanc. And the Large Hadron Collider is 27 kilometers of circumference, and it accelerates and collides known particles that are the protons. We're made of protons. We're colliding particles we know. But then what happens to these collisions? You need something to see the products of these collisions. And so there's experiments that record and analyze the products of these collisions. And I'm pointing out the main 4 ones. And they are actually in different countries. So there's one in Switzerland and 3 in France, because there's also a border there. How big is this? And this is really large. Like you can see it in it encompasses the entirety of the center of Manchester if you put the LHC as a ring on top of Manchester. You can also try it yourself. We can circulate the links later on, and you can try to put the LHC around your city. And the experiment that I work on, the Atlas experiment, is huge, both in terms of how many people work on it. It's more than 3,000 people now. But it's also in terms of dimensions. It's a 46 meter for 25 meter kind of machine. It's a lot of double-decker buses that you can stack in the experiment. And this is something that we use to see the products of the collision. So we start with protons. We profit from E equals mc squared. So we put energy into the protons, and we create particles that are more massive than the protons. That's what we think that dark matter, this WIMP, might be. We want to create these dark matter particles. And the energy that we put into the EMC square is provided by the LHC, where protons are accelerated. And the range of the mass the mass of the dark matter particles is that in the reach of the LHC is around 1 tera electron volt. Sounds a lot, but it's not a lot. We can talk about that in the Q&A. But it's in terms of particles, it would be the biggest particle we've ever seen. So I'm going for a very brief video of how we actually do these collisions. So let me press the button. Okay, so this is a zoom into the Geneva area and an aerial view. Now we're getting underground, 100 meters underground, where the accelerator and the experiments are. And this is 27 kilometers circumference tunnels with 4 huge experiments. Where the particles are seen after being accelerated to 99% the speed of light. And they complete a lot of turns of this ring every second because they go so fast. And now we're following the path of one particle, and boom, that's a collision. That's how collision of particles look like. It lights up some pieces of this giant digital cameras that is the detector, but it does it really fast. There's 600 million collisions every second. So this is how we're trying to make dark matter. Maybe one of these lines, well, actually not these lines, we'll see why there's a trick there. Maybe the content of this collision can tell us more of what dark matter is. So we've seen before that there's a detector, and this is our Atlas detector, and it's able to catch or see all the visible particles produced by the collision. So if you have a collision of protons that produces visible particles, you have no problem because you know where the visible particles are gone. You have tracks, you have deposits of energy from these particles, so you can reconstruct track of these particles. Now, what we know about dark matter is that it's invisible to the detector. It's dark, it doesn't interact very much. And this means that we have no idea if we just put 2 protons together, if we just have a dark matter generated in these collisions, we don't know where it's gone. And it's effectively invisible to the detector, so we need something to make it visible. And the solution is that it's very rare that the dark matter particle is made by itself, or even 2 of them. So we use other visible particles from the collisions and look for what is missing. And you can think about it if you've done a little bit of physics. Maybe some people in the audience will have seen that in their education, that we have conservation of energy. You expect to put in a certain amount of energy and get a certain amount of energy out. It's the same. You shouldn't lose any. And it looks like if you have dark matter, you're losing some because you can only see the visible part. And so this missing energy, more technically missing transport momentum, is how we see dark matter. So if you rotate the detector to look into it, like as if we were a proton, I'm actually in my background, there is the detector and we're actually looking into it. Well, we're looking out of it at the moment. Anyway, you have the cross section that is this round here, and you see that you can balance by eye where the arrows go, and the arrows is an indication of the direction and the amount of energy that each visible particle has. So you see the visible particles going on one side, the invisible particles are going on the other side. All you see is the orange arrows, or are the visible particles. And you can imagine, if you forget about the invisible dark matter particle lines, that there needs to be something else balancing the visible particles. And that's the missing transverse momentum that we infer from conservation of momentum or conservation of energy. So we are trying to count how many of the collision events have an excess of the missing transverse momentum with respect to what we know from the predictions of only the known matter. That's what we're trying to do. That's how we're trying to see dark matter. And this is, if you take the detector away and just keep the tracks and the energy deposits that I was mentioning, you see that there's this big disparity between something that is really large. There's a lot of energy, a lot of tracks going in one direction. This is the yellow and the green. Those are the visible particles interacting with the detector. And then there's nothing on the other side. Those are the invisible particles coming out. And the challenge for us is really distinguishing the invisible particles that are coming from dark matter and the invisible particles that are coming from the standard model. Because you've heard about the Nobel Prize from Professor McDonald, it's about neutrinos. We have neutrinos, and we can produce them as well. So it's hard to distinguish them. You'll see more about that later in the next talks. Anyway, finally, I just wanted to leave you with just some food for thought and something that segues into the next talks. That's great. So can the LHC look at dark matter, create dark matter, discover dark matter? And sure, it can create dark matter, but I don't think it's able to discover dark matter only on its own. It needs also all the other experiments that are out there. And today we'll hear about direct detection, where you shake dark matter, and the indirect detection, where you break dark matter, because these are experiments that are able to see dark matter from the sky and can tell us if we're seeing the same thing. They answer the question of how do I know if an invisible particle that I see at the LHC is dark matter since I created it? We need to see it from space as well. But the complementary advantage of making dark matter at the Large Hadron Collider is that we have known initial ingredients. So we can explore really the interaction that happens between the known and the dark matter. So we can create new particles. So I would say I leave you with let's keep looking for these new particles at the LHC and together with the other experiments to look for dark matter. Thanks a lot for your attention.
Wonderful. Thank you so much, Caterina. Hopefully you will be able to see me in a moment. Fab. Great. So thank you so much, Caterina. That was really, really interesting. Next up, we have Alberto Olivier. Alberto is an astroparticle physics researcher of the INFN. He is a senior scientist of the AMS2 collaboration, an experiment that has been running on the International Space Station since 2011, able to detect high energy particles produced in the cosmos, the so-called cosmic rays. He's here to tell us more about how we're trying to find dark matter by breaking it. Over to you, Alberto.
Hi, happy Dark Matter Day to everybody. I'm so happy to be with you today. I will try to share my slides just in a second. Can you see and hear me clearly?
Yes.
Okay, thank you very much. So I've been assigned with this topic of how to break dark matter. But I will not talk about everything about this subject because it involves many different techniques. And I will, however, specifically talk about how we do this search, especially using cosmic rays. And at the very end, I will mention also other ways that other experiments are able to do this interesting topic of the indirect search of dark matter. So to explain this, I have to do a step backward and first of all, try to explain what are cosmic rays. So basically, what's happening is that Caterina, before me, explained the marvelous Large Hadron Collider, where we are able to accelerate particles up to very, very high energy. That is the most powerful man-made accelerator. But in the cosmos, there are, let's say, machines, accelerators of particles that are even more powerful than the LHC, that are able to accelerate this particle to energies far beyond what we can do here on ground. And these particles that are accelerated by these processes, as an example, by the supernova shock wave, but many other mechanisms are out there. This particle accelerated to high energy that are arriving from the space, from all direction. These particles, we call them cosmic rays. So these cosmic rays here on ground, we are basically kind of protected from this high energy radiation because we have the atmosphere. So that on the atmosphere, we have the impact of the cosmic rays. They get destroyed into particles that are much less dangerous than an high energy proton. But however, they arrive to ground in form of muons, most of all, that are not very dangerous, but many of those are arriving. So if you want to observe the cosmic rays clearly, you have to go up, and maybe with balloons, stratospheric balloons, or as in our case, we go to space. We go to the International Space Station that is 400 kilometers above the Earth to observe cosmic rays directly. So what are cosmic rays? Cosmic rays are essentially, since these are basically some kind of matter that is accelerated by this explosion and stuff like that, are basically matter. So there are all components of matter there. There are protons, because the proton, the hydrogen is the most common element in the universe. So most of them is just a simple hydrogen nucleus, the proton. We have also all the other nuclei of the periodic tables inside the cosmic rays in a smaller portion. And we have electrons. So all this stuff is the usual matter. But then in the cosmic ray with very small fraction that are of percent level or fraction of percent, we may have the positron, that is an electron with the plus sign, so is an electron with the opposite charge, is the companion of the electron, is the anti-particle is said to be of the electron, and antiprotons that instead are the respective antiparticle of the proton. So why we have antimatter in the cosmic rays? This is the basic question, because if you look around, you don't see much antimatter. Maybe Caterina, she's more used to antimatter. They produce a lot in LHC, but usually you don't see in these percentages the antimatter around you. So why in cosmic ray instead we see this antimatter? So that's the idea here. So we can produce antimatter in the cosmic rays in several ways. One way, let's say, is the standard way. So we can have normal cosmic rays, matter, like protons, electrons, etc., accelerated somewhere. They stay in the galaxy. They interact violently, like what happens as an example, proton-proton in the LHC. This is similar. It's a proton of high energy coming from acceleration in the supernova, going toward a proton that is steady in the galaxy, an hydrogen nucleus that is just there, and they do a collision, and there is a production of many particles and also antimatter of high energy. So one thing is a kind of standard production. This we call normally secondary production. So this is the first source of antimatter that we can foresee. Then it's possible that in the dark matter halo, this thing that has been discussed at the very beginning by Art, in this halo that we need, no, because otherwise the galaxies are not in balance, they would get completely different curves of velocity. In this halo, it's possible that steady state particles that are basically steady, dark matter particles that are basically steady, may self-interact, may annihilate with each other, and produce standard model particle, like a couple of electron and positron, or like a couple of proton and antiproton, particle and antiparticle. These are produced at some energy because these particles are quite massive, this WIMP particle. So as an example, the electron and the positron are produced basically with an energy that is similar to the mass of the particle, of the dark matter particle. So it's possible that dark matter annihilation, they produce this component of antimatter and matter in the cosmic rays. Finally, there is also another source. There are objects, known objects, like the pulsars, that may produce, as an example, couples of electrons and positrons. Pulsars are very fast rotating neutron stars. They have huge magnetic fields, and in this environment, it's possible to produce electron-positron pairs. So we have these sources. Okay, so this is the main picture. So we can detect dark matter by break it. It means that somewhere this dark matter gets destroyed and transforms into particles that we can detect. That's why it's indirect, because we don't see directly dark matter, but only the products of it. So how we do the separation between matter and antimatter? Then this is a key point for this research of dark matter in cosmic rays. So here, as I said, one thing is to get out of the atmosphere. So that's why with my experiment, we are on the International Space Station that you have also behind me. That's the International Space Station, 400 kilometers above the Earth. On this station, basically the residual atmosphere is very small, and our detector is just on the truss of this space station that is long by about 100 meters. And here inside the circle you can see even the letters of AMS, and this is our experiment. It is quite big for the space standards because it's 3 by 4 by 5 meters cube. And how we do the detection of matter and antimatter in this detector? Basically, inside AMS there is a big magnetic field and particles with different charge. This is what distinguishes particle by antiparticle, is just that the charge is opposite. So in the magnetic field, the particle just bend in with a different curvature. We can reconstruct the curvature by the measurement of the position of the particle in several places, and we can split between electron and positrons. Of course, you need many more devices because you want to be sure that this is an electron, that is a proton, this is an helium nuclei, that is a deuteron. So you need many other things. But the essential ingredient of this experiment, the Alpha Magnetic Spectrometer, is the magnetic spectrometer. So the magnetic field and the distinction by curvature. So with AMS, we did extensive studies because AMS is on the International Space Station since 2011. So we have already over 10, we did just this year 10 years of data taking in May. We did some party about that, in fact, even if we are in COVID times, so with some restriction. And however, with 10 years data, you can see this positron flux. This is the measurement of how many positrons we collected as function of the energy. This is a graph. What is interesting in this graph is that the famous positron coming from collision, as predicted by the models, so the standard component of the positron, is the part that you see with this color, with the blue color. This is a general behavior, let's say, of the most common models of the cosmic rays. We can do the prediction of this because we know the fluxes of protons, we know the fluxes of all the matter that is in the cosmic rays, we know how much material there is in the galaxy, we know how much time the cosmic rays stay in the galaxy. All of this is extracted from other studies that we do with the other cosmic rays, and this, however, can be calculated. So it remains a huge excess. AMS has been, this excess is known since some time. Some time ago it was known as the heat excess, then as the Pamela excess, and nowadays is the AMS excess. And AMS has been able to measure this excess of positrons up to very high energy. In fact, now we see a shape there. And the shape let you believe that this may be dark matter, because you would expect something that is a bell around the mass of the dark matter, the dark matter particle. However, it's possible that we are seeing other things like pulsar, contribution from pulsar, and many other things. So to know this, definitely you need more information, like directionality, because if it's a nearby pulsar, maybe these protons are coming mostly from one direction, or maybe you can take a look to the electrons, how they behave, and many other things, or take a look to the antiprotons. I will not make a seminar about AMS here, but this is just to give you an idea of the things that you can do with the cosmic rays. But the cosmic ray is not the only way that we can do the break-it of the dark matter. In fact, the dark matter can self-annihilate to many kind of particles. They can transform into anti-nuclei, like antideuteron and deuteron, two couples of antideuteron and deuteron, and we will have a balloon experiment that we will study this. Also, IMS can do that, but we will have a dedicated balloon experiment in the near future. It can produce gamma rays, and this is a huge field. I just put here Fermi because it's a very well-known mission that did a lot of stuff in the gamma ray field, but experiments like HESS on ground, CTA in the near future will do a lot of studies about this, but the list is very long, and I'm not making any justice in describing this field. And also in the neutrinos, it's possible that dark matter annihilates in couples of neutrino and antineutrino, and detectors on ground. In this case, I just put here ice cube that is in the South Pole, and this is an underground experiment. This is studying this kind of indirect production of particles from dark matter. So there are a huge number of activities in this field, and I really believe that we in the near future will be very exciting. And thanks everybody for the attention and having me for this presentation. And here there is AMS. Take a look to our webpage and keep going.
Fantastic. Thank you so much, Alberto. I have popped that link in the chat, so hopefully everybody will be able to see it, and you'll be able to have a look at that. And we are now live on Facebook, so thank you to those that have stuck with us. We have finally made it, the joys of technology. So thank you, Alberto. If anybody does have any questions, please do pop them in the Q&A. If you've got any comments, that would be lovely to hear from you. Now, before we take a short break, we have one final talk from Jita Hall to tell us about shaking dark matter at SNOLAB. Jita is the Director of Research at SNOLAB. He has experience working on a number of direct detection dark matter experiments, and in his current role ensures the lab's research program continues its tradition of supporting high quality, cutting edge astroparticle physics. There we go. Jita, over to you.
Thank you so much, Lauren. And thank you everybody for coming. It's very exciting to be here. First, I did want to apologize to everybody who expected me to get up and dance for 10 minutes. It's not that kind of shake it. So today, this talk is about the field called the direct detection of dark matter. So by direct detection of dark matter, what we mean is that this dark matter that you've seen talked about for the last 40 minutes, 50 minutes, may come into our labs on Earth and may rarely scatter off of normal matter. This is a beautiful picture made by Mike Atisha showing what's supposed to be normal matter, say a crystal, and having particles, various particles come in and scatter off the nucleus or come in and scatter off the electrons. So there are many dark matter candidates. Some of them we do believe may rarely scatter off of nuclei. Some we believe may rarely scatter off electrons or interact with the electrons in interesting and new ways. The challenge that we face in this field really is that there are many known types of backgrounds. So there are many known types of radiation. You can see it on this plot. that Mike Atisha has made. So you can see he talks about photons or electrons, which we call gammas or betas, scattering off of electrons. We also have neutron radiation that we know about, and this will also scatter off of nuclei, creating signals that look a lot like what we expect dark matter to look like. So really, this field is very focused on basically removing all of these known types of radiation that we see in the world and that we know about in the world and that we've been studying for the past 130, 140 years and trying to find the unknown as we get rid of all the known types of radiation. And so that is the field of direct detection of dark matter. Now, I've been waving my hands a lot and talking about invisible energy in the air and how we can detect it with crystals. So sometimes I like to show actual pictures just to give a little feel for what I'm talking about. So this is a cloud chamber. This is really actually a climate science project. So you can see lots of little droplets of liquid in the air. So you just set up a chamber where you have a liquid that's evaporating and raining back down, much like on Earth where we have the water cycle, although here you use alcohol. And by doing that, you can form clouds. And so this is what they were doing in the late 1800s, trying to study cloud formation, atmospheric phenomena. And this is what you start to see when you turn on such a cloud chamber and look at the clouds you're forming. You see these short tracks. These are the first ones you might notice. These are alphas. So we gave it the first letter because they're the easiest to notice. There are other tracks that you will see here. These are betas and then also gammas. For example, this is a piece of thorium, and you can see many more tracks coming off of this piece of thorium. It's used in welding, for example, and you can see a lot more radiation coming off of it. This is good evidence that thorium is a good nuclear fuel. And so it's really observations like this that led to all of nuclear and particle physics. And really, you can see here, understanding the materials and the radiation properties of materials is also important for us. The betas coming off this thorium, for example, will be thinner tracks streaming off of it. And the gammas are even harder to notice because they actually go through all of this gas without interacting. So you need other detectors to really study those. I could sit here and watch these movies all day. So background radiation, hopefully I'm convincing you so far that background radiation does mask dark matter events in the experiments that we're trying to observe, where we have a detector and we're looking for dark matter interacting, creating one of those tracks perhaps. Now you saw that movie, that was in real time. So you can see the rate of the natural background radiation or the rate from materials that we see in real time. Now, the experiments we're trying to build underground, we want to run those for 3 to 5 years with no background events at all over that time period. And that's an extreme challenge for us. So we have to specialize in building low background detectors. And by that, I mean building these radiation detectors out of materials that don't themselves emit radiation. So all the materials that we use to build these detectors are measured for radioactivity. That's a big part of what we specialize in. We can see tiny amounts of uranium or thorium in almost anything because we have to construct these experiments. Additionally, as we construct them, you can see a picture on the left here of somebody working on one of these low background dark matter detectors. This is TEEP. As you construct this experiment, you have to be very cautious about dust, dirt, and even radon getting in the detector. So the dust and dirt are handled by being in a clean room. The radon is a different story, but also something that we specialize in and try to understand the sources and how to mitigate and remove from our experiments. And finally, as Alberto was saying, the cosmos hosts sources of high energy backgrounds. So I like to show a couple of pictures from NASA. This is a picture of M87. This is one of our neighboring galaxies. This one's actually a pretty massive galaxy, and it hosts a supermassive black hole in the center, something that's a billion solar masses or so, we think. And you can see that when this black hole is active, it just shoots out these amazing streams of the highest energy radiation we know of. And this radiation will wander through space and it will hit the Earth's atmosphere and cause backgrounds. Additionally, a little closer to home is the Crab Pulsar. This is a star that exploded in 1054 from what we believe. And you can see in X-rays in blue, the electrons just circling around this black hole in this Polarion. You can see electrons coming out of the, this pulsar, electrons circling around the pulsar and electrons coming out of the pulsar Polarion. And this radiation also will wander through our galaxy and then hit the atmosphere. As Alberto said, when it hits the atmosphere, it will create these massive showers of particles. This is an artist's rendition. These showers of particles will even sometimes hit the ground with scales of hundreds of meters wide, and they'll be kilometers, many kilometers long, sometimes the entire depth of the atmosphere. And these are very tricky backgrounds. Some of the particles that are made, these are these muons, and they're very penetrating particles. And so that's why dark matter experiments are sited deep underground to avoid these backgrounds. So I think that's a good introduction as to why we are such clean freaks in the direct detection of dark matter business, because we want to get rid of any source of dirt, which will end up putting radioactivity in our detectors, and why we go underground. It's to hide from these black holes and supernova that are causing way too much interference with what we're trying to do. So hopefully next you'll see a journey into the underground to see what these laboratories look like. And thank you all for listening.
Amazing. Thank you, Gita, so much. That was really, really interesting. And hopefully all of those talks that you've just seen have given you a great introduction to dark matter and how we are going about looking for it. So do keep your questions coming in using the Q&A box. We will now be taking a short break until just past 1/2 the hour. So that's just past 3:30 in the UK and just past 10:30 in Canada. And if you're elsewhere in the world, 1/2. After which we will travel underground to tour our 2 incredible and unusual laboratories. So we will be visiting the STFC Boulby Underground Laboratory first, and then visit SNOLAB. And I'm so excited to see these tours and meet some of the fantastic people that work there. Now, you don't need to leave the session. We will just switch off our cameras and mute our sound, and then we'll just start back up just after 1/2 the hour. So we'll give you a couple of minutes to grab a drink and maybe switch on some lights if you're in the UK, because it's getting pretty dark, and we will see you then. See you in just after 1/2. Goodbye. So hopefully you've had time to grab a drink and some refreshments before we carry on with our journey to learn more about dark matter by heading deep underground. Now, the first lab that we are going to visit is the STFC Boulby Underground Laboratory. It is the UK's deep underground science facility located 1.1 kilometres below ground in Bulby Mine, a working potash, polyhalite and salt mine in the northeast of England. Now, Bulby is a special place for science, enabling a wide range of studies requiring access to the geologically interesting and ultra-low background deep underground environment. Science at Bulby ranges from low background astroparticle physics to studies of geology, geophysics, climate, the environment, planetary exploration technology development, life in extreme environments on Earth and beyond. Now, before I hand over to the team in the lab, I just want to share with you a little video of a journey underground, which is a journey similar to the one they have taken today. And I just really like this image here. You can see at the very top, we have got where the mine is, and then the shafts to get underground to the laboratory. So let me head over to this video. Fantastic. So I'm going to click play, and then there we go. And then I'm going to talk over the top. There's no sound, but you will just hear my voice. Let's go. So you can see everyone on the surface getting ready to go into the mine that you can see in the background, including Chris, who is filming, and you'll meet him later today. Now, this group are heading to the surface building to take them underground. Now, you've probably noticed that there's no lab coats at this stage and that everyone is wearing bright orange suits, helmets, ear defenders, and other personal protection equipment. At this stage, they're heading to the lift, known as the cage, that takes them down to pit bottom in the mine where the underground lab is located. Now, Chris is just showing you one of his tallies. This is what they use to make sure that they know who is in the mine. So you hand one in on the way up, down, and one when you come back up. Now, the cage ride takes 7 minutes to travel the 1.1 kilometers underground, and it only goes at very specific times. If you miss it, you have to wait for the next one, which probably won't be soon. And it's really sad if you're like Chris yesterday, ended up down in the lab for quite a long time and forgot his lunch. Now, once you reach pit bottom, it's about a 10-minute walk to get to the lab, but luckily we've sped it up for you in this video. The layers of rock that you can see are left over from the evaporation of an ancient sea called the Zechstein Sea about 230 million years ago, and those mine tunnels stretch much further than you can see on this short walk. Now, away from the cage area, it gets very dark, so you can see everyone's got head torches on their helmets. Now, here we are coming up to the lab entrance and into the door inside the lab. Fantastic. So here is where I am going to stop my share and hand over to Emma, Chris, Ed, and Shin in the mine. But before that, I just wanted to introduce Emma. So Emma is the senior science technician at the STFC Boulby Underground Laboratory. She heads up the science support team, manages and operates parts of the facility called Bugs, and manages the public engagement, outreach, communications, and well-being for the lab. She has been part of the team at Bulby since 2010 and won the IOP Technician of the Year Awards in 2019. So Emma, over to you.
Thanks so much, Lauren, and thanks everyone for joining us today. So welcome, this is the Bulby Underground Laboratory, and as that video and Lauren just explained so nicely, we are 1.1 kilometers deep here, and this lab's been operating for quite a long time now, but I've been here for 12 years, and in that time we have had 2 separate sites. So this is our second site in my time, but in actual fact we've had 4 separate sites here. So we're going to give you a bit of a tour today. There's a whole team of us down here who are going to give you the tour, and I'm just going to start by telling you a little bit about the lab itself. So this lab is quite large, and it's very, very clean. So the mine that we're in, you're going to see a little bit about that later, but it's a very dusty environment, as you can imagine. It's surrounded by salty rock. And so in order to have our very sensitive detectors running in here, particle detectors and some other kinds of machinery, we need to make sure that we keep it very, very clean. So our lab is actually 2 separate clean rooms. We have a class 1000 ISO 6 clean room, which is what I'm sitting in now. We have a class 10,000 ISO 6 clean room, which you're going to see very shortly. And because it's a clean room, we have to wear very special equipment. So normally scientists, you expect them to be in a lab coat or, you know, looking very sciencey, but in actual fact, if you're going to be a scientist, a technician, an engineer, or any other member of staff down here in our lab, and probably in SNOLAB, you're going to have to wear a different set of clothing. So you can probably sneak a peek here. I've got some bright orange clothes on. I have a white tie back over the top. This is a clean room suit, my hairnet, gloves, and hard hat. And all of the miners underground here have to wear lots of PPE. And then if you're a scientist or a technician or an engineer working in the lab, we have to wear exactly the same PPE as the miner. And you saw on that video those belts, we wear them all the time. I'm wearing mine now, and everybody else is too, with all of our kit. As well as that, we work very hard to keep the lab clean, not just having a whole team of people keeping it clean. We have a very special person, Maria, who works for us, who keeps this lab super clean, but we have some technology that helps. So we use air filtration systems called HEPA systems. They're huge, and all of the air that comes into the lab is filtered through that. And then the air is very controlled, over pressure to stop dust getting in from outside. And we monitor that all the time. So we have lots of specialist equipment, particle monitors. We monitor our temperature, our humidity, our radon levels, and various other things here in the lab. And all of that's done and collated so that we can constantly keep a check on our environment to make sure that it's absolutely optimal for science. What I'm going to do now is I'm going to actually start talking to a colleague of mine who's with us today, and we're actually very lucky that he's here because he's not here all the time, but Dr. Shinran Liu has worked with me since 2013, I think, He did a master's and a PhD with us, and he's now a fully-fledged doctor, and he does a lot of analysis and work here in our books lab. So I'm going to hand you over to Shin to tell you a little bit about the work that is going on here.
Hi, well, welcome and thanks for joining me in the Bulby screening facility. So I'm super excited to give you a little tour of our lab here and tell you a little bit about what myself, Emma, and the technicians here at Bulby do at the Bugs facility. So I think I'm going to start off with these detectors you can see behind me. So I think my particularly own personal favorite is the loon head detector. So the reason that we are in this lab and why this lab exists is that we live on planet Earth, but our planet is unfortunately a radioactive planet. So everything you see around us, you can touch or feel, has some levels of uranium and thorium. I don't want to panic anybody out there, but the level is tiny and it doesn't pose us any dangers. But even that tiny, minuscule levels of radiation, when they get into our dark matter detectors, can mimic dark matter signatures that we don't want. So we want to minimize the amount of radiation in the materials we use to build our detectors. And to that end, we created these 3 different types of wonderful detectors you see in this lab. I'm going to take you through each one of them. So why Loonhead is my favorite, as you already heard from Emma, is that I've been coming here since 2013. And when I first came to Bulby, we had just one germanium detector, and that was Loonhead behind me. And all these detectors have wonderful names named after local mines in the Bulby area. But yeah, so since Loonhead, which was the first detector I got to work on, we've rapidly expanded to have now 7 germanium detectors. And the way these detectors work is that they measure gamma radiation in the uranium and thorium decay chain. So at each point, as the uranium and thorium decay into daughters and subsequent daughters, some of them emit gamma radiation, and that by measuring that, allows us to work out how much uranium and thorium is in our sample. And the reason we have 7 is that each of them specializes in different kind of gamma range of gamma energy. So some are really great at measuring very low energy gammas, whilst others are much broad range, or some have very specific. If you have very small samples, they're really optimized to measure small samples at very high sensitivity. So yeah, that's why we have such a range of detectors. And these detectors have been essential. And just from here in this room, we've measured components for dark matter detectors around the world. In particular, the experiment I worked on is called Lux Zeppelin. And the detectors here have all been screened almost half of the components that went in to construct that dark matter experiment. So, yeah, so it's really been a great international effort. And these detectors have been instrumental in building the next generation of dark matter detectors. Right, so I think now we're going to look at the next 7 detectors. So these 2 are called XIA Ultralow 1800, and they're alpha detectors. So what they detect is alpha on the surface and bulk of materials. So what our materials typically look like, it's a very thin sample. They're usually very clean. So we insert them into our detector, and we leave it to measure for days, weeks, depending on how radioactive they are. And the reason why this is important is, well, not only do we want to choose material that doesn't contain a lot of uranium and thorium, but also often when you leave your sample out in your room, you have radiation in the air that can stick onto the detector. And then over time that builds up. So we want to find out ways to kind of clean our sample of any radiation that's stuck out on the surface. So in the future, when we build dark matter experiments, and at the very heart of the detector, we want to find ways to clean any radiation that's going to build up in the heart of our detector. Okay, so then we have one last detector to show. So the last one is a radon detector. And why this one is particularly interesting is that in this uranium and thorium decay chain, radon is a noble gas, and it poses the biggest problems for many dark matter experiments out there. Because being a noble gas, it's very inert, it doesn't interact, and it's very hard to get rid of. And it can just it lives for a long time, and it can just go through various materials. So we have to measure radon, the rate radon is emitted very carefully. So we're just currently the plans are underway to build 2 radon detectors. These will be world-leading radon detectors when they're done. But noticeably, they do not yet have a name. So if you have a great idea for a name, do send them in, and we'll definitely give it some consideration. Okay, so that is it from me here at the Bulby screening facility, and it's over to Chris and over to you, Lauren.
Brilliant. Thank you so much, Shin and Emma. Hello, everyone. I'm Chris. I can very happily say that I have remembered my lunch today. I'm well fed and ready to go. Welcome to the main hall of Bulby Underground Laboratory. I'm a facility scientist. I've worked here for about coming up 8 years now, so fairly long in the tooth. And first of all, I'd love to tell you about all the science we do. We do a lot of science in this laboratory, but it's dark matter day, so I'm obliged to talk about dark matter and all things that apply. So behind me, you can see a whole host of experiments. Shin and Emma have just done a great job telling you about why we're underground. We're underground to get away from all that background radiation, same as what Jeetu was saying in his talk. There's just radiation everywhere. And it's not even enough to come down here and get so clean. Even after you've designed your wonderful experiment to be as clean as possible using the bug screening facility, you come down here, you install your detector, and you still need to protect it further still. So behind me, I'm going to switch my cameras, bear with me. Behind me, we have something that we call a castle or a cave, and some people call it cave or a castle. And what this is, in essence, is yet another shield to get away from background radiation. So what you're looking at are great big blocks of stainless steel, but what's actually inside those stainless steel casts are molten lead. And that molten lead solidifies, and then each brick weighs about 2 tons of lead. And lead is a brilliant shield to protect it against further radiation. So inside this detector, in this castle, is yet more detectors that care about being away from radiation. And actually what this used to house, if we're going back in the history books, is the Zeppelin detector. So what you can see here on the floor is actually part of the Zeppelin detector, this being here. We're thinking about turning it into a coffee table, but for now, this used to be the Zeppelin cryostat. But Zeppelin was one of our most famous programs. The Zeppelin program ran for a number of years. It had 3 generations that increased in size and technology over the years. And Zeppelin, as you'll hear over and over again, is one of the pioneering techniques for dark matter detection. And simply put, it used a great big vat of liquid xenon, xenon being the element. You can cool it down into the liquid phase. And when you have a great big vat of it, it does this special thing where when it finds a particle, it gives you a flash of light, but then it gives you a second flash of light. So it gives you 2 flashes of light. These flashes of light we call scintillation events. And by comparing the energies of these scintillation events, it gives you a really good tool for looking for dark matter. And so this is really what puts us on the map. And it set one of the best dark matter limits for a number of years back in the day. But no good staying in the past. We've got to keep on moving. And we're going to go to some of our current, oh, by the way, here's Tony. He is our health and safety manager. Brilliant, because of course, health and safety and science is an alliance. And then we move on to our current detector. So we have 2 here actually. So quite in contrast to Zeppelin, which was as big a vat as Zeppelin, as liquid xenon as you could muster, these 2 are actually the complete opposite end of the spectrum. Instead of having a great big vat of heavy stuff of dark matter to bump into, these are actually 2 gas detectors, and they're similar and different in equal parts. So what you see on the right here is the News G detector, and on the left is the drift or Cygnus detector. So I'm going to talk about drift very quickly first. So again, you can see this great big vat of white stuff. That's actually, again, a castle. This time, instead of having lead as your shield, we have water and plastic. Ultimately, what we care about is a high hydrogen content, because hydrogen is really good at blocking those neutron backgrounds that Jeetu was telling us about. So actually, the detector is housed deep inside that castle of plastic. So what's interesting about gas detectors is that they give you an extra level of discrimination. So drift, or Cygnus as it's now been taken over into a larger conglomeration, is a directional dark matter detector. So unlike Zeppelin, that gave you a flash of light and then a second flash of light, drift actually wants to tell you where the dark matter came from. So Zeppelin tells you that you've seen something, drift or Cygnus will tell you where that thing came from. And that's interesting for one big reason, because we think that the way that we move in our universe, in our galaxy, is, well, we're always orbiting in the same direction, we would hope. But if dark matter behaves how we think it will, it shouldn't move with us. It should be almost like stagnant air that we are moving through. And so if we're moving through it, relative to the dark matter, we should have a direction. So all the dark matter events, if we see any, should come from one direction. And that's not the band, I mean, literally from one point in the sky. So what you can do is you can add up all of your dark matter signals, and if they're all coming from one point in the sky, you can rule out with pretty clear confidence that that is dark matter, and it's a really powerful tool. So to build a good dark matter detector, you need a couple of things. You need to have a lot of stuff for the dark matter to bump into, which is why Zeppelin was good. Or you need to be really good at, it's something called discrimination, ruling out your backgrounds, comparing what you do know to what you don't know. So NEWS G, which is this beautiful sphere here, and this is the first version. There's going to be a larger version coming soon, which will be 3 meters diameter, hopefully, is very much the same technology. Again, it's a sphere in that vessel filled with gas, and depending on if a particle interacts, you'll get some level of ionization. So unlike Zeppelin that gives you scintillation, which is the flash of light, in these gas detectors, you're getting ionization, which is where electrons will be pushed out of nuclei from interactions. So what you're looking at here is a smaller version, and it's very much the same process of drift, but instead, by going to a sphere, you get a really nice uniform electric field, which helps in a number of ways, but also it gives you a really good look into low dark matter, so low mass dark matter. So you'll have heard again from a number of talks today that there are many, many different things that could be dark matter. Some of them are very light, some of them are very heavy. And this particular method is a really good way of looking into those very light dark matter particles. So I'm going to briefly stop there, but I've told you about our current experiments. And I'd love to tell you more about the lab, but what I'm going to do now is use our deepest underground flushing toilet. And so while I do that, I'm going to hand over to Ed, who is outside. So far I've told you about this wonderful clean space. We've got it right away from radiation. And I've told you we're a mine, but you wouldn't think it by looking at this lovely clean space. So I'm going to head to the toilet. I'm going to let Ed tell you more from the mine. Thanks, guys.
Thanks very much, Chris. That might be a little bit too much information for sharing, but I appreciate it anyway. So yeah, welcome outside. Hopefully you can hear me all right. I say outside, but we are still actually 1.1 kilometers underground underneath the northeast coast of England in these mines. You might notice that I'm rocking the full orange outfit, fantastically visible with the reflective strips. I've also got all my safety gear on. So I've got hard hats, safety glasses, steel toe cap boots, and even shin guards. So this is because we are actually in an active mine. They are mining further out under the sea and over to the east as well, so somewhere off in that direction. What they're mining for is a type of rock salt. Some of the salt that they mine, they actually use to de-ice the roads in the winter, but the majority of it is used as fertilizer in agriculture. It's a type of mineral called polyhalite. For the majority of the duration of the mine's existence, it was mining potash, which is another type of rock salt also used as fertilizer. So where's this salt come from? This salt was left behind approximately 230 million years ago when there was a sea where we're now standing. This sea was called the Zechstein Sea, and it extended from the northeast coast of England over the current North Sea and into the north coast of what's now Germany and Poland. Over time, this sea evaporated, and because it's a sea and it's salty water, as it evaporates, it leaves all the layers of salt behind. And over the process of millions and millions of years, that salt gets compressed further down and further down, and that's where we're now standing. Fortunately for us in our experiments, where they're actually doing the mining is miles away, literally miles. The tunnels extend for hundreds of kilometers, not in a straight line, in a kind of spider web pattern. There's over 100 kilometers of tunnels in total. The actual mine face is about 10 kilometers away. They have to use vans to drive through the tunnel to get there. It takes about 45 minutes. For us, you've already seen the little video. It only takes us about 10 to 15 minutes to walk through the tunnels to the laboratory. But still, the conditions are quite different to what you'd expect on the surface, or maybe what you'd even expect from a mine. It's very hot down here, currently about 35 degrees C. Where they're doing the mining, it can get as hot as 45, even a little bit hotter. It's very dry, it's very salty. You've got to make sure you've got water with you if you're working down here. But it's these conditions that allow us to do lots of different types of science. So primarily we come down here to do dark matter studies, and it's the rock above our heads that's fantastic at absorbing all these cosmic rays and all this different type of radiation, which lets us use a very quiet environment, radioactively speaking. But also, it would be a shame not to make use of the fantastic environment that we have access to. So we actually do a whole range of different experiments. Chris has shown you past them in there. We've got experiments looking at radiocarbon dating, how life reacts to low levels of radiation, but specifically using the rock. We have some experiments looking at using the rock here as large-scale energy storage. So in a similar way to how currently when we have an excess of energy on the grid, maybe it's a very windy day and wind turbines are providing more energy than we currently need, we can use that energy to pump water to the top of a reservoir. And then if we need that energy at a later date, we release it, it turns a turbine. The same idea can be applied with gas. So you can compress gas into caverns in the rock and then release it at a later date when you need the energy. So we're doing some experiments right here, drilling holes, testing how the rock can be used for that. But possibly, well, another exciting experiment that we do is testing Mars rovers and space exploration techniques. We have a yearly event called MINAR. MINAR stands for Mine Analog Research, remembered it just about. And because of the very dry conditions that we've got, the very strange atmosphere, but also because we're in a tunnel left behind when a sea evaporated, that's actually quite similar to what we think the surface of Mars or the subsurface of Mars might be like. We believe that there used to be water on the surface of Mars that has since evaporated. So surprisingly similar conditions. So every year we get scientists from NASA and the European Space Agency and all sorts of other agencies and universities. They come down here, they bring their test Mars rovers and test projects that are going to be going on different space exploration missions and different ways of looking for life in these very dry, very salty environments, because it's just about the closest that we're going to get to Mars on the surface of Earth. I'm going to just quickly walk around here. I've got Sean behind the camera, who's our laboratory director. So you can see the entrance to our laboratory. The tunnels are maybe not as claustrophobic as you would expect for a mine. We've got about 3 meters height and about 8 meters wide. This is a fairly standard tunnel. How they drill them, they've got these massive machines that just drill out, as they go, and they make this spider web of tunnels. And we decided to use one of these disused tunnels to build our laboratory. You can see the entrance to it there, through to the very clean side where my colleagues were earlier. I've been banished to the outside, dirty side as usual. But this is where some of the fantastic science goes on as well. So hopefully that's given you a quick overview of our facility and some of the different types of science that we do here. It's primarily dark matter, but it's not just dark matter. We've expanded into all sorts of different things. I'm going to pass you back now to Lauren. Thanks very much for joining us deep down under the North Coast.
Amazing. Thank you so much, Ed. They were fantastic. And it was so lovely to hear from Emma, Chris and Shin as well. Now, next up, we're going to go even further underground to 2 kilometers underground to SNOLAB. SNOLAB is Canada's deep underground research facility, research laboratory located in Vales Creighton Mine near Sudbury, Ontario, Canada. It provides an ideal low background environment for the study of extremely rare physical interactions. SNOLAB's science program focuses on astroparticle physics, specifically neutrino and dark matter studies, though its unique location is also well suited to biology and geology experiments. SNOLAB facilitates world-class research, trains highly qualified personnel, and inspires the next generation of scientists. We're going to be hearing from Blair and Pierre. So Pierre Gorel is a research scientist at SNOLAB. He has worked on neutron decay and neutrino experiments in the past and currently focuses his efforts on direct dark matter searches as part of the Deep 3600 and NewsG collaborations. I'm just going to share a little introductory video and then hand over to Blair and Pierre in SNOLAB. So let me share my screen. And hopefully you can see this lovely introduction. Third time lucky. Wonderful. So that was a little bit of an introduction so you can see how they get into the mine as well. I'm now going to hand over to Blair, and she will hand over to Pierre when it's time. You may need to adjust your sound at some points in case, because they are quite far underground. So if you can't hear them, just turn them up. So Blair, over to you.
Thank you so much, Lauren. We've just had a great tour of Bulby facility. That was wonderful. So for our next stop, we've had to come all the way over to Canada. We've traveled deeper underground. We're now 2 kilometers underground here at SNOLAB. That's about 6,800 feet. Now, like Bulby Lab, SNOLAB is also located within an active mining environment. We're located in Valley's Creighton Mine in Sudbury, Ontario, and this is an active nickel and copper mine. So we've got our 2 kilometers of Canadian shield overhead, providing great reduction in muons and other high energy particles that are coming from space. But the area that we're surrounded by, so the rock, the dust, the dirt, that's all a source of backgrounds for our experiments. So we operate our whole facility here at SNOLAB as a clean lab, and we're a class 2000 clean lab. So what that means, if you imagine a cubic foot of air, so here at SNOLAB, in a cubic foot of air, there's less than 2,000 particles that are half a micron in diameter. Half a micron is about 100th of the width of a human hair, so super tiny. But what does that really mean? How might it compare to your home, your office, maybe your school? That sort of location that you might be watching from today has about 10 million, or about 1 million particles per cubic foot of air. Out in the mine drift, where we've just come from, there's about 10 million particles of that size per cubic foot of air. So we really spend a lot of our time and energy and resources cleaning our air to create a space for low radiation studies. So everything, that's a bit about the air, everything coming into the lab needs to be cleaned. And that includes actually the people. So here at SNOLAB, we walk into, it takes about 20 minutes to walk into our facility from where the lift drops us off, and we take a full shower. So when I walked in today, I was wearing my mine gear, and it's very bright orange as well. And when I got into the facility, I got into the change room, I hung that up, and I took a full shower. So a full hair wash, and I put on a fresh set of clean lab clothing. So that includes the blue suit that I'm wearing. You'll notice everyone that you see today will be wearing the same kind of outfit. It's a low lint fabric. So that's the people. The materials coming into our lab also need to be cleaned. And that happens in our cleaning facility that's called the car wash. And that's where I'm located right now. So I'll pick you up and I'll actually turn my camera around. So this facility gets the special name of the car wash because the side, so it's a 2-car facility, and the side that I'm showing you through the window actually opens to the mine drift. So you see the rail cars. The rail cars are here. They have been pressure washed. We have overhead cranes in this area. So all of the heavy duty cleaning happens on that side, the dirty side of the car wash. Now, the side that I'm on, this is the clean side of the car wash. And this is where the fine detail cleaning happens. So my camera equipment, for example, would have been cleaned on this side today. So I show you this area because it's really quite important in that every single item that you will see on the tour today came through this very same area and was cleaned here. So that's everything from very tiny bolts and screws for experiments to very large items. Everything comes in through this area. So with that, I will, actually, before I send you over to Pierre in the cube hall to start looking at experiments, I will say that our whole space here at SNOLAB is 5,000 square meters of clean room space, all kept at class 2000. And we have many different experiments. So we have experiments studying neutrinos, low background techniques, we have biology, and we have a lot of dark matter. So since today is all about dark matter, that's what we'll focus on. And with that, I will ask Lauren to send you over to my colleague Pierre in the cube hall, and we'll start checking out experiments.
Pierre, are you there to switch your video on? And I will head over to you. Are you with us, Pierre? Green, I think he might have dropped out because 2 kilometers underground can be very difficult to connect. So I'll just pop back on me for a moment. If anyone does have any questions that we can answer, then I think that would be really, really good. So we've had some really, really fantastic questions coming in. Blair, I'm gonna replace you as the spotlight because it's always nice to see where you're going.
Yes, and I figured I would just walk over. So I'm just traveling through our clean room facility now. And I may drop off as I go through this area, so just bear with me. I'll come right back on. So as you walk, you can see, you know, the wall. This is our blasted out rock, and it's been painted with this low radon paint. You can see all of our services running overhead. I'm actually just walking to the direction where Pierre is. So we've got industrial items as well.
So I believe we've got Pierre back again.
Oh, fantastic.
There we go. Just connecting to audio. Fantastic. Pierre, are you with us? Possibly. Pierre, can you hear us? Give us a thumbs up if you can. We can see you, which is very exciting. I think you might be muted.
Are you now talking to me? Of
Fantastic.
course, it's the moment the button is passed. It's the moment where the cell phone decides to just drop the connection. So I'm going old school and I'm going with my laptop instead.
Perfect.
Okay. Hi, everyone. So I am Pierre, and I'm a scientist here at SNOLAB. And I am, well, actually not anymore that far away from Blair because she, in the meantime, she had time to move pretty much to the other side of the lab. But I am actually much deeper than she is because I am at the moment at the bottom of a cube hole, which is one of the 3 experimental caverns at SNOLAB. So the size of a cube hole is about 20 by 20 by 20 meter, which is in height at least the equivalent of a 4-story building. The other experimental hall or caverns, there is the cryo pit on the other side over there, but at the moment there is activities and a fairly dirty activity happening, so we are not going there. And the Snow Plus cavern, which is completely on the other side of the lab, and because it's not dark matter, we are not going to go there either. Anyway, as far as the cube hole is concerned, so one of the things that is a bit annoying with dark matter experiments is that you usually don't see them because they are within the shields. And most of the time they are actually sensitive to light, so we don't want to have them open. So it's fairly disturbing. So from time to time, we actually manage to do something like a big picture like that to show what's inside the tank. But most of the time, what you can see only is the external shield. So what Chris was showing earlier at Bulby was a particular kind of shield with using lead or using polyethylene blocks. Here at SNOLAB, we like to use water. So water is a very good neutron shield and a okay gamma shield. And the thing is that it is relatively cheap. It's non-toxic. Most of the time, it's considered even not really dangerous. And you can use it in in a lot of quantities because here in the mine, we use water. The mine actually uses water as a way driving force for drills and things like that. So basically they use a lot of water and we can use a lot of water also. So in our case, we purify that water as well as we can. Actually, it is purified such that it is considered an insulator. There is nothing left in that water except H2O. And we fill it into those big tanks. Of course, in order for those tanks to be watertight, we use liners. The steel that you see around is mainly for structural purpose. So this particular tank that you see here that is open is in fact the one that contained the dark matter detector mini-clean until recently. Mini-clean has finished its operational life, so it is now being dismantled. That's the dirty work that is happening on the other side, because now that it is the detector doesn't have any use anymore, it is basically cut into small pieces so that the pieces can be brought back to surface. But on the other hand, this detector here, this shield here contains the deep 3600 detector. So here normally contains about 3.6 tons of liquid argon as active material to look for dark matter. So liquid argon is a scintillator. So we will see that flash of light Chris was mentioning earlier. Argon is a fairly good material for the dark matter detection. Maybe not as good as xenon, but it has different properties. And one of the very good thing about argon is that it is much cheaper than xenon. So you can make it in a very big quantities, make very big detector only for a small fraction of the price you will do for a xenon detector. So what you see basically on that picture is the external part of the detector. So one of the nice things about using water is that it can be seen as an active veto. So we are going underground in order to get rid of most of the muon coming out of the cosmic rays, but some of them are still making it underground, and we want to make sure that we actually detect this so that we can remove them from our data. So the water tank is used in that case as a Cherenkov detector. So when the muon passes through, it has enough energy to emit Cherenkov light. So and that light is detected by all the photomultipliers that you can see under that picture. So around that ball of stainless steel. And the detector itself for dark matter is inside the stainless steel, away from the water, and in the case of deep 3600, it is the liquid argon is contained into a shiny acrylic ball. Now the last detector that we have in the cue ball is actually NewsG as well, but this particular NewsG is the intermediate state between the small sphere Chris was showing at Bulby and the 3 meter sphere that is hoped to be deployed in the future. So this one, again, within its shield, what you see, also it looks like stainless steel. In fact, it's just the outer part of a big polyethylene shield to remove neutrons. And inside that polyethylene shield, we have a big lead shield to protect from gamma rays. And inside you have a 1.4 meter diameter copper sphere that is actually the detector. So filled with gas. Actually, at the moment, we were just pumping on it, so it is totally empty. But I will refill the detector later today. So we have actually three technologies here. Also, mini-clean is gone. This particular location is going to be used for the next Pico 500 detector, which is a detector using superheated fluids. So superheated fluids is basically a think geyser. You are going to heat a fluid higher than its temperature of its boiling point, and then it's enough that there is a small amount of energy deposited in the fluid, and you will have a creation of a bubble. So the idea is that the dark matter particle is going to make that small deposition, and then you can add a single bubble, and you can look at that bubbles with cameras, and you can listen to the pop of the bubble to figure out what kind of energy it was and what kind of particle created the bubble. So we will have here a superheated fluid here we have a liquid argon scintillator, and here we have a gas detector using scintillation, not scintillation, sorry, ionization. So we have completely different technologies, and the idea of using those different technologies is to prevent to get what we call the detector bias or systematic problems. So if you see the dark matter on one detector, but you don't see it on the next detector, despite looking at the same part for the same kind of particles, then there's a probability that what you see is not dark matter, but in fact an artifact of a detector. Now, if you see it on multiple detectors and at the same with the same characteristics, then there is a good chance that what is seen is genuine dark matter. And I think I'm going to pass it to Blair back to on the top of a detector, and I'm going to walk to a different place.
Awesome, thank you. So we just saw some really large scale dark matter detectors with Pierre over in the Cube Hall. I'd like to highlight some of our smaller detectors that are using some really cool technologies to search for dark matter as well. So what we can see here is the Sensei Experiments. So we see the white shielding. So this is a water tank shielding that is just being completed in its installation. And we can look at the lead bricks that are here. And inside that lead castle is the detector. So the Sensei detector uses CCDs. So there's also another detector down at the end of this hallway called DAMIC, which also uses CCDs for dark matter detection. CCDs are charged coupled devices. So that might sound familiar from your digital camera or your phone. So those are tiny CCDs. These experiments use very large scale CCDs. So some of those are developed for telescopes, and Sensei uses a special type of CCD called a skipper CCD. Skipper CCDs allow for the individual electrons in a pixel to be measured, and it allows for really precise particle detection with very little backgrounds. Members of this collaboration actually received a breakthrough prize in physics for the development of this new type of CCD technology. The other interesting piece about this experiment is that the construction actually happened during the pandemic. So the team at Fermilab, largely based at Fermilab, who was planning to come and install their detector at SNOLAB, they had to pivot with the pandemic, and they've been instructing a team of our scientists and technicians to build this detector. So it's quite a niche example of international collaboration across borders. So how this experiment works is when we have a dark matter particle or any particle collide with the silicone in the detector, it deposits a charge in the pixel of that. And we can see that Pierre is just walking over to the ladder lab. So I'll walk down and I will show you a little bit of the DAMIC detector, because the shielding for this one is off as well. So both of these experiments are using CCD technology, and both are using lead and this poly shielding that you can see here. So like many of every experiment, we have layers and layers of shielding protecting those. And I think with that, I will get ready to hand it over to Pierre, and we're going to check out a few more experiments over in our ladder lab.
So I'm hoping that we will see Pierre, but there is a possibility that the connection has dropped again.
And that's quite all right. I'm going to walk over to that area of the lab.
Marvelous.
It's called the ladder lab, and that's where our cute and super CDMS, a couple more dark matter detectors are located. So let's see. Now, as a heads up, when I walk into this area, my Wi-Fi may drop for just a moment, but bear with me and we'll pick right back up.
No problem.
Here we go.
So I believe, Pierre, you're back with us. Fantastic. We've just got 1 or 2 more minutes for you to finish. Thank you.
I am not very lucky with connections. Okay, so here we have additional work happening here. So what I can show here is the Pico 40, so the smallest size of what eventually is going to get in the cryopet. So it's still under work. They are actually trying to prove a concept before they go for a much bigger version of it. So what you see on the far side is the water tank for it, and just as I'm walking by is the inner vessel, the outside vessel for it. So where you can see actually the place where the cameras are going to be mounted in order to see the bubbles appearing inside. So the fluid, in order to be seen, is inside a quartz enclosure, which is not underground yet, which is still under being either built or being cleaned somewhere. But what I'm passing beside now is basically where the new super CDMS is going to sit. Hello, Blair. So what is visible already is the seismic platform that will support the detector itself, and on the far side, the clean room and radon depleted room. So as you heard, dust is a problem, but radon is also a problem. So we need to both, every time we work on this kind of detector, we need to both being in a much cleaner environment than the lab is normally, and additionally, the radon level in the air needs to be completely decreased. So that's why they have a special room for that. Beside that, they have what they call the CUTE facility, which is a testing facility for the super CDMS towers. So only the super CDMS detector is in fact made of several towers of smaller detector, and the idea is to be able to remove one tower at a time, put it into a dedicated system so that they can test, characterize the tower all by itself without having to worry about the other detector nearby. So once again, they have a full shield with water, and inside additional lead and copper in order to protect the detector. Actually, the fridge has been removed because it is under maintenance at the moment. So it is visible inside their own smaller clean room here. And that's all for SNOLAB. Handing over to you.
Brilliant. Thank you so much to both of you. That was really interesting. And I would have loved to stay much longer looking at all of the fantastic things going on there down at SNOLAB. I have popped some things in the chat for you. But now I think we have got time to put a few questions to our panel. So if you are on the panel, please pop your camera on and I will spotlight you. Fantastic. So our first question, just while I am adding everybody to the spotlight. Fantastic. So we should have everybody now. Brilliant. So our first question is about potentially for people at SNOLAB and people at Bulby. It says, who actually builds all of the experimental kit? I imagine the scientists design and use craftsmen to assemble. Who would like to answer that?
I can answer it from Bulby's point of view. I'm sure it's very similar to SNOLAB, but they can probably answer as well. But actually, in our lab, the experiments are built by a mixture of scientists, engineers, and technicians. So we have many of the astroparticle physicists who work on the dark matter experiments are experimentalists. That means that they design and build experiments for this purpose, as well as understanding the theory and such like. And then they're supported by a team of engineers, project managers, and technicians. And I'm pretty sure it's similar to SNOLAB, but I'll pass over to Gita for that.
Yes, that's right. I think, you know, the design, as you said, is a combination of both the scientists and the engineers, and sometimes the technicians, because particularly you see a progression of some of these experiments, and even the technicians have knowledge to bring to the design. On the construction side, I think it's a wide variety of occupations that are required to make this come together. You know, we have the mining company at SNOLAB that gives us access, and there's a dedicated group of excellent people, you know, keeping the shaft going and the lift to bring us underground and making the mine in general safe and monitoring for seismic activity. As we go into the laboratory, we have cleaners, and they're extremely important to our experiments, to cleaning all the materials, tradespeople, to put together the experiments in coordination with the engineers and scientists. So it's quite a combination of different trades and jobs to really get these experiments together.
Amazing. So we are nearly out of time, so I will ask a few more questions because I think there are some fantastic ones. So if anybody does want to stay for a minute or two more, you can, but we have our fantastic speakers have been answering the questions in the Q&A, so you can have a look at those. And because this is the first time we've run this event, we'd love it if you could fill out our feedback form. I've popped that in the chat as well. And we also have a Dark Matter Ask Me Anything webinar happening on Monday. So do sign up for that if you have any more questions. So the next question I would just like to share with you, it says, hello underground people. I really like that. Do you have to give up eating Brazil nuts and bananas to work there? AKA, how radioactive are people, and is that a problem? Who would like to answer?
Here in bugs, Brazil nuts and bananas would be a problem for us if they were on our detectors, because then they have a very high potassium level. So potassium 40 is a radioactive isotope of potassium. In fact, Bulby here has plenty of that in the rock, because that was something that was mined here for a long time. And that is a gamma emitter, which gives off quite a big gamma. So it causes not just a great big spike in your data, but a whole backwash of noise that we just don't want. If we put bananas or Brazil nuts on our detectors, we would see all of that. Us eating them isn't going to really cause a problem. I mean, the only time anything like that is likely to cause a problem if we started, like, I don't know, licking the end of the detector or sweating into it or something. But generally, they're so well covered and such like that. We can pretty much eat what we want. We are generally the most radioactive thing in our labs beyond our purposefully made radioactive sources, but we tend to keep that pretty much well to ourselves, unless, like I say, we're sweating on stuff or touching stuff. I don't know if Gita has more to add to that.
No, I thought that was a brilliant answer.
Amazing. Thank you, Emma. Now, Emma, I know you have to catch a ride out very, very soon. So if you need to leave, that's absolutely fine. I just had one more question that was for Katerina, but other people might answer it as well. It says, when do we think that dark matter was created in the Big Bang? And what WIMP energy does this infer? And how does this compare to the LHC-1 TeV proton collisions? So Katerina, you answered that really, really well by typing. Would you like to share a little bit more?
Sure. It's a bit long of an answer, so I'm not going to read it. I'm going to try and summarize it. But I think it really depends on, so we know how much dark matter is there right now, right? That's 27% of the overall. How you got to that, what kind of theories and what kind of interactions made up and made it come to 27%, basically define what kind of dark matter you're looking for. And right now, there are some, if you it depends on what you're thinking. You could believe a theory better than another theory, or you could look for an experimental excess and say this is more promising than this other experimental excess. But I think we're still a little bit in the dark. Sorry for the pun from this. So I wouldn't say that there is a specific preferred mass range. There's a nice plot that shows how many orders of magnitude, and I'm talking about tens with many, many zeros around it, there are for both how often the dark matter interacts with standard matter and how massive the dark matter is. And there's a number of theories that fill this space, but we don't know what the preferred theory is. So I wouldn't say the LHC is going to find it first, or this other experiment is going to find it first. We have to look everywhere. So it's not very satisfactory. Sorry, I can't give you a better answer and saying this is it, but I don't have a favorite theory at least.
Absolutely fine. And then just one last quick question. I say quick, it's not really very quick, but Vincent has asked, hi, if I correctly understood something after the sentence, dark matter day, make it, break it, shake it. The main idea about shake it is to prevent all already known interactions due to matter in order to find interactions due to dark matter. Did you already have noticed some interactions that you couldn't explain, and how to conclude whether an unknown matter / dark matter interaction or dark matter interaction? GT, you look like you're typing an answer to it, but if you would like to take the floor, or Alberto, if either of you would like to begin to answer.
This is a shake it question, so I leave.
That's okay.
Yes, Alberto did give an example though in the antimatter, the electrons, the positrons excess. So we have seen many signals that we couldn't explain at the time, or we still can't explain. We often call these anomalies because we're not confirming that these are dark matter. We have no confirmed observations of dark matter, but these are exciting and interesting observations when we can't understand our detector. And so we typically have follow-up analysis, follow-up measurements, and follow-up experiments even to understand these things. And these happen throughout particle physics. There was just a talk yesterday on sterile neutrinos, which came up, I believe, which was quite interesting, which was a follow-up and an anomaly. This is how we spend a lot of our time. And you know, I think really isolating unknown signals and then understanding them is what we spend a lot of our time on, and how we hope to conclude that something is actual dark matter interactions rather than somebody got a drop of sweat inside the detector.
Fantastic. I think we will stop there now. Thank you so much, everybody. I'm just going to share my screen one last time to share with you our upcoming Ask Me Anything event that's happening on Monday. So hopefully, if you have any more questions, or you've got some, you'd like to learn a bit more about dark matter, do come along to that. We have some fantastic speakers that are ready to answer any of the questions that you might have. And the final thing that I wanted to say was just a massive thank you for joining us. Thank you to all of our fantastic panelists and all of our staff working along in the background to make everything run. We really are grateful that you've been able to come along, and to you as the audience, thank you for coming to join us with our Dark Matter Day. Make it, break it, or shake it. We'd love your feedback. If you do want the recording or to have any of the answers to the questions that have been asked, please do drop us an email. I'll stay on this webinar just for a moment so you can get all of the links that you need. But that's it from me. Thank you for joining us. And remember, don't be afraid of the dark. Goodbye.